On the night of the 15th of December, 1811, a Scottish naturalist named John Bradbury was asleep on a boat moored against the bank of the Mississippi River. He was a fellow of the Linnean Society, traveling the interior of America collecting plants. He kept careful notes. 6 years later, he published them, and what he wrote about that night is one of the best accounts we have of any earthquake anywhere. In his words, about 10 o'clock, and in the night, I was awakened by the most tremendous noise, accompanied by an agitation of the boat so violent that it appeared in danger of upsetting. He got up on deck. He could see the river, in his words, as if agitated by a storm, and although the noise was inconceivably loud and terrific, he could distinctly hear the crash of falling trees and the screaming of the wild fowl on the river. Then the banks began to fall. Perpendicular banks, above and below them, collapsing into the river in such vast masses as nearly to sink the boat by the swell they caused. By daylight, he wrote, they had counted 27 shocks. This is the beginning of the most powerful earthquake sequence to strike the contiguous United States east of the Rocky Mountains in recorded history, and it happened in a place with no fault line anyone knew about, 1,000 kilometers from the nearest plate boundary. The first shock came at about 2:15 in the morning, local time, on the 16th of December. Estimates of its moment magnitude range from 7.2 to 8.2. Its epicenter was in what is now northeast Arkansas. The future site of Memphis, Tennessee was shaken at intensity 9 on the Mercalli scale, the scale that measures not the energy released, but what the shaking does to people and buildings. Shaking of intensity 7 or greater, enough to damage ordinary buildings, was observed across an area of about 600,000 square kilometers. 6 hours later, at 7:15 in the morning, a second shock of magnitude around 7.4 struck. Contemporaries called it the daylight shock. It was similar in intensity to the first. Then, on the 23rd of January 1812, a third, magnitude estimates from 7 to 8, in the Missouri Bootheel. Its area was marked by general ground warping, ejections, fissuring, severe landslides, and caving stream banks. And on the 7th of February at 3:45 in the morning, the largest of all, magnitude estimates run from 7.4 to as high as 8.6, with an epicenter near the town of New Madrid, Missouri. The town was destroyed. In St. Louis, well over 200 kilometers away, many houses were severely damaged and their chimneys toppled. The maximum shaking intensity observed in that final shock was 12, the top of the scale. Total destruction. Now here's what makes these earthquakes genuinely strange, and it is not the magnitude. It is how far away people felt them. The shaking was felt strongly across roughly 50,000 square miles, and moderately across nearly 1,000,000 square miles of the central and eastern United States. For comparison, the 1906 San Francisco earthquake, one of the most destructive in American history, was felt moderately over about 6,200 square miles. The first shock rattled windows and furniture in Washington, D.C. It rang bells in Richmond, Virginia. It sloshed well water and shook houses in Charleston, South Carolina, and knocked plaster from houses in Columbia. In Jefferson, Indiana, furniture moved across the floor. In Lebanon, Ohio, people ran out of their homes. Observers in Herculaneum, Missouri, called it severe and reported it lasting 10 to 12 minutes. Perceptible shaking reached as far as Canada. One writer noted the shocks continued for years in Illinois and, writing in 1855, said some had felt them that very year. There is a physical reason for that reach, and it is one of the most important ideas in this episode. It has to do with what the ground between you and the earthquake is made of. Near a plate boundary, the crust is broken up, faults of fracture stacked against each other, and every one of those boundaries scatters seismic energy. The waves fade with distance far more quickly. In the middle of the North American continent, the rock mass is old, cold, and continuous, uninterrupted by fractures or faults over enormous distances. It carries seismic waves the way a struck rail carries sound. So a New Madrid earthquake rings the whole eastern half of a continent. A Californian earthquake of the same size does not. Same energy, entirely different reach. Which raises the obvious question, why is there an earthquake there at all? New Madrid sits in the middle of a tectonic plate. There is no plate boundary within 1,000 kilometers. Earthquakes inside a plate are called interplate earthquakes, and they are rare compared with the familiar kind at plate boundaries. They are also, for a specific and unpleasant reason, disproportionately dangerous. Because buildings far from plate boundaries are rarely designed to resist shaking, nobody retrofits for an earthquake that has never happened in living memory. The list of damaging interplate earthquakes is a list of places that did not expect them. Gujarat in 2001, Christchurch in 2011, Charleston in 1886, and New Madrid. Gujarat is the sharpest lesson. It occurred far from any plate boundary, in a region that was completely unprepared. In the Kutch district, the death toll passed 12,000, the total was above 20,000. So why does the middle of a plate break? The answer under New Madrid is a scar, something ancient, buried, and never quite healed. Beneath the Mississippi alluvial plain lies a feature called the Reelfoot Rift, a place where the continent once began to tear itself apart and then stopped. Accounts of its age differ. Some place its formation in the breakup of the supercontinent Rodinia, around 750 million years ago, others in the Cambrian. What is agreed is that the rift failed. The continent did not split, but the structure stayed buried as what geologists call an allocogen, a scar, a zone of weakness, deep underground with faults and old igneous rock in it. Today, North America is drifting west, and that motion puts a relatively small east-west compression on the plate's interior. Small, but a weakness needs only a small push. Other ancient rifts exist in North America and do not produce earthquakes, so something more is going on here. One suggestion is heating deep in the lithosphere, making the deep rock more plastic and concentrating the stress into the shallower rock above. The honest position, stated plainly in the literature, is that the underlying cause is not well understood, which is a remarkable thing to say about the source of the largest earthquakes in the eastern United States. What we can describe precisely is what the shaking did to the ground, and the mechanism responsible has a name: liquefaction. Loose, sandy, water-saturated soil is held up by nothing more than grains touching grains. Water fills the gaps between them. Under normal conditions, the grain contacts carry the weight of everything above. Now shake it hard, repeatedly, faster than the water can drain away. The loose grains try to compact, the water pressure between them rises, and at some point that pressure exceeds the force holding grain against grain. At that moment, the soil stops being a solid. Its strength drops essentially to zero, and it behaves like a liquid. Ground that held a house a second ago now behaves like quicksand. This is not a historical curiosity. Liquefaction wrecked San Francisco's Marina District in 1989, the Port of Kobe in 1995, and thousands of homes in Christchurch in 2010 and 2011. In 2018, on Sulawesi, liquefaction buried a suburb and a village 3 meters deep in mud. The Indonesian government considered designating both neighborhoods as mass graves. In 1811, along the Mississippi, liquefaction is what destroyed the village of Little Prairie in the very first shock. The ground it stood on simply stopped being ground. Where the pressurized water found a way up, it erupted, carrying sand with it and spreading it across the surface. These are sand blows, and they occurred across Missouri, Tennessee, and Arkansas, burying farmland. At Lake St. Francis in eastern Arkansas, sand and coal were ejected from fissures in the swamps as water levels rose 8 to 9 meters. Whole tracts of land dropped. Others rose. Fissures opened. Landslides ran. Riverbanks collapsed. Islands in the Mississippi vanished entirely, and boats were washed ashore by waves on the river. And in Tennessee, the ground subsided by between 1.5 and 6 meters, and the water came in and stayed. That is how Reelfoot Lake was made. It is still there. It is a shallow, swampy lake famous for its bald cypress and its nesting bald eagles, and it has been a national natural landmark since 1966. Before 1811, there was no lake. There was a river, the Reelfoot River, identified in a land survey begun in 1785, described in 1797 as about 30 yards wide. A February shock on the Reelfoot Fault pushed one side of the ground up over the other. That uplift blocked the streams. The water backed up behind it, and the drowned forest is still standing in it 2 centuries later. Which brings us to the famous part. Everyone has heard that the Mississippi ran backwards. It is the detail that survives in the popular memory. So, did it? Eliza Bryan in New Madrid wrote her account in March 1812. She describes the roaring of the Mississippi, the current of which, she wrote, was retrograde for a few minutes. Her explanation was that it was owing, as is supposed, to an eruption in its bed. And she was, broadly, right. Several things happened at once. Uplift along the fault created temporary waterfalls on the Mississippi at Kentucky Bend. Water piled up behind them and waves propagated upstream. A seismic seiche, a standing wave set off in a body of water by the shaking itself, ran up the river. Local uplifts of the ground and the side of waterways moving upstream gave observers the impression the river was flowing backwards. So, not the whole river reversing for hours, as the legend has it, but locally, briefly, genuinely, water moving the wrong way, exactly as people on the water reported. It is a good example of how eyewitness accounts and physics fit together. The witnesses were not exaggerating. They were describing, accurately, a thing that happened for a few minutes at their location. Eliza Bryan's other account is worth hearing in full because it captures what these nights were like. She describes a violent shock accompanied by a very awful noise resembling loud but distant thunder, but more hoarse and vibrating. Then, she wrote, came the complete saturation of the atmosphere with sulfurous vapor, causing total darkness, the screams of the affrighted inhabitants running to and fro, not knowing where to go or what to do. The cries of the fowls and beasts of every species, the cracking of trees falling, the roaring of the Mississippi. A scene, she concluded, truly horrible. John Reynolds, later the 4th governor of Illinois, remembered it as a boy. His family slept in a log cabin. His father leapt out of bed shouting, "The Indians are on the house." They laughed at his mistake, and then found it was worse than that. Not one of them knew, at the time, that it was an earthquake. It took the next morning's shock for them to work it out. He remembered the cattle coming home bellowing with fear, the house cracking and quivering, chimneys thrown down across the American bottom, and the church bell at Cahokia rung by the shaking of its own building. The death toll is unknown, and always will be. The region was a sparsely settled frontier, communication was poor, and record-keeping was worse. The buildings helped. Predominantly wooden structures resisted collapse. They cracked and racked rather than falling. Most deaths seem to have come from chimneys, falling trees, and drowning as subsided land flooded. A Methodist chaplain traveling with Andrew Jackson in 1813 wrote in his journal that the fissures produced in the earth about Madrid look awful on both sides of the river, and that fears are ascertained that the worst is to come. He recorded that there had been about 1,000 inhabitants in the town of New Madrid before the earthquake, and that at the time of his writing, there were only about 300. The people who lost most in this were not the settlers. Cherokee settlements along the St. Francis River were flooded and abandoned, and the Cherokee moved to the Arkansas River Valley. And the earthquakes entered politics immediately. They were interpreted by Tecumseh's Pan-Indian alliance as a sign that Tecumseh and his brother, the prophet, must be supported. The timing mattered. Tenskwatawa, the Shawnee prophet, had just been defeated at the Battle of Tippecanoe, and Prophet's town had been destroyed. Then the earth shook the whole continent. For many, that vindicated his teachings and his brother's warnings. It is one of the clearest cases in American history of a geological event changing a political one. Now the question that matters today. Was 1811 a freak, or does this happen on a schedule? The answer is written in those sand blows, because they are datable. Sand erupts, buries the ground surface, and buries whatever was lying on it, including artifacts left by people living there. Dig down through a sand blow, find what is underneath, date it with carbon-14, and you have a maximum age for the earthquake that produced it. Do that in many places, and a pattern emerges. Previous large earthquakes, like those of 1811 and 12, appear to have happened around 1450, around 900, and around 300 Anno Domini, with evidence for an apparent series around 2350 BC as well. Southwest of the modern zone, near Mariana in Arkansas, two sets of liquefaction features have been tentatively identified and dated to 3500 and 4800 BC, again interpreted as groups of large earthquakes closely spaced in time. There is a second archive, and it is alive. Bald cypress trees in Reelfoot Lake carry the 1811 event in their rings, fractures, followed by rapid growth after their inundation. In the St. Francis sunklands, cores from old bald cypress show the opposite, growth slowing for the half-century after 1812. Both are clear signals of the same event, recorded by trees standing there when it happened. And here's what those rings say about the quiet years. The tree ring record at Reelfoot Lake goes back to 1682, and in the St. Francis sunklands to 1321. Neither shows another signal like 1811, which is evidence of absence, used properly, no big New Madrid earthquake between those dates, and 1811. The gaps are real, and they are long. There is a further wrinkle. Uplift at the rate implied by these earthquakes could not have continued over geological timescales without dramatically changing the landscape, and it has not. So, either the seismic activity here is young, no more than 64,000 years old, or the earthquakes and their uplift migrate around the region over time, or the zone has short bursts of activity separated by long dormancy. Any of those is unsettling in its own way, and none of them says the zone is finished. The zone is certainly not quiet now. Since 1974, the epicenters of more than 4,000 earthquakes have been identified from seismic measurements in the Reelfoot Rift. Most are tiny. The largest since 1812 were in 1843 and 1895, with magnitudes estimated at 6.0 and 6.6. The 1895 event near Charleston, Missouri, damaged virtually every building in the town, made sand blows beside it, cracked a pier on a railway bridge, and toppled chimneys as far away as Memphis and Evansville. In 2003, the United States Geological Survey estimated a 7 to 10% chance of a major earthquake like those of 1811 and 12 within the next 50 years, and a 25 to 40% chance of a magnitude 6 or greater. Those are not small numbers. A 1 in 3 chance of a damaging earthquake in a region where almost nothing has been built to survive one is a serious problem. In 2008, the Federal Emergency Management Agency warned that a serious earthquake in the New Madrid seismic zone could inflict the highest economic losses due to a natural disaster in the United States. The report predicted widespread and catastrophic damage across 8 states, and noted that in Tennessee, a magnitude 7.7 or greater would damage tens of thousands of structures, affecting water distribution, transportation, and other vital infrastructure. The thing that keeps engineers awake is not the magnitude. It is that continuous, unbroken continental rock, the same property that rang bells in Virginia in 1811. The same earthquake that would damage a few counties in California would, here, reach across 8 states at once. And underneath it all is a rift that failed 750 million years ago, or 500, depending on which reading you take, and never fully closed, being squeezed by a continent drifting west a few centimeters a year. That is what deep time actually means, in practice. Not remote, not finished. A structure that stopped forming before there were animals, still loaded, directly beneath a modern American city. John Bradbury counted 27 shocks before dawn on a boat tied to a riverbank in 1811. The ground he was moored to has been doing this, at long intervals, for thousands of years, and it has not stopped.